The goal of this whole section is just to understand, like, why is carbon with 4 hydrogens around it tetrahedral? Why is carbon linear in carbon dioxide with 2 double bonded oxygen? And when it comes right down to it, we need to explain how atomic orbitals, these are the 1s, 2s, 2p kind of things. How do you take those orbitals and make molecules? And this is actually a more important question than you might at first think. The circle part right here is an s orbital, and there's no angles associated with it at all. And the other 3 pictures right here are all different p orbitals. And if you remember, p orbitals are kind of like a figure 8, and they're at 90 degrees from each other. So one is x, one is y-axis, one is z-axis. But how the heck do you take these types of orbitals, which at best have 90-degree orientations with them, and s's don't even have any angles at all? How the heck do you turn it into tetrahedral CH4, which is what that picture is on the right? And remember, a tetrahedron has 109-degree angles. There's no 109-degree angles in the atomic orbitals. So these theories we're going to look at in this section will try to describe how you go from the atomic orbitals into essentially the orbitals in molecules. And again, there's 2 theories to explain this. The first one, and arguably the best one, is called molecular orbital theory. It was developed by a scientist named Mulliken, all right, and it's really cool. In a molecular orbital theory, you can actually take the atomic orbitals and do some cool things with them. In molecular orbital theory, which is sometimes abbreviated MO theory, the valence electrons around atoms are delocalized. And what that means is those electrons, they don't just exist on the individual atoms. They make like a energy shield, if you will, around the molecule. The picture on the right is a BH3, and the little green kind of, I call it shields around the ship, but I like a lot of Star Trek, okay? But anyway, those shields are made up of the valence electrons. The valence electrons literally are delocalized over the whole molecule, so it is kind of analogous to shields on the starship. And if you're not a Star Trek fan, first of all, I forgive you. It's okay. But second of all, I'm just joking about that. You don't have to like Star Trek to do well in this class. But shields were put around a spacecraft to protect it from things like meteors and, of course, other spaceships firing at them, stuff like that. So it's a kind of a cool analogy here for what's going on in molecular orbital theory. Those valence electrons are placed in a type of an orbital like they were in atomic orbitals. But in this case, they're placed into a molecular orbital, all right? And the molecular orbitals are essentially delocalized, i.e. spread around like peanut butter on toast over the whole molecule. Now, MO theory is really cool, but MO theory is also pretty complicated, as we're going to see. So we're going to look at some examples. Arguably, one day in the future, when computers become more and more compact and you have more of a phone kind of computer next to you, MO theory will dominate. But in the meantime, we do need to think about the other theory as well. The other theory is called hybridization theory or valence bond theory. They're the same kind of thing. Sometimes I will probably abbreviate this VB theory for charity. Anyway, Linus Pauling, who we talked about in the last chapter, who discussed electronegativity, was the proponent of the valence bond theory. And valence bond theory is pretty cool. Valence bond theory is something that you can literally do on the back of an envelope. You don't need a sophisticated computer or anything to figure out the results of valence bond theory. In valence bond theory, those valence electrons, which were spread over the whole molecule in MO theory, those valence electrons are localized between 2 atoms, or lone pairs for that matter. So instead of being spread over the whole molecule, like peanut butter on toast, the peanut butter is literally just spread between the 2 atoms, the atoms that are sharing it. If you have a lone pair, then those electrons just sit on that one atom. So it's a little bit different kind of model. In a valence bond theory model, you have 2 half-filled atomic orbitals, and they combine, they overlap to make bonds. So we're going to come back to the idea of what exactly sigma bonds is, and later on pi bonds, stuff like that. Pretty cool. So in this theory then, electrons are stabilized by 2 nuclei. The electron might have started on carbon, but then it's stabilized between a carbon and a hydrogen, or a carbon and another carbon, or something like that. This picture is something we looked at briefly in the last chapter, but we'll look at it here in more detail. This shows the ideal description of what a sigma bond is. And remember, sigma bonds are when atomic orbitals combine. They smash into each other, they go head to head, and the interaction between them is what makes the sigma bond. So this is the interaction between two s orbitals. If you look over on the far right here, each of these little spheres is an s orbital. All right, so imagine you have two, say, hydrogen atoms, and they want, if you will, to form a bond. Well, as the atoms get closer and closer, so you can see here they're closer and here they're even closer yet, then the electrons begin to form that sigma bond. And there will be some ideal bond length and some ideal bond energy, which represents the most stable form of the H2 molecule coming together. However, one thing we didn't talk about in the last section is that if you go even closer, all right, so this little picture right here shows that as you go even closer, then you begin to have the electrons repel the other electrons more, and the nuclei repel the other nuclei more. So you begin to get to the place where you don't have any energy savings. And remember, in physical science, it's all about the energy. We probably want the ideal energy, which would be right there, and that's going to correspond to an ideal bond length, which is right there. As you get too close, you lose that, all right? It becomes unstable. It's like if you stand really close to your friend, like really, really close, or you're in their personal space. It kind of freaks people out, all right? That's kind of the equivalent here with two atomic orbitals. They can get too close to each other and kind of freak each other out.
The energy of two atoms varies with distance, according to the interplay of the attractive and repulsive forces between them.
So again, this video just shows again how there's a place, an ideal distance where you have the most energy savings, if you will. You really store a lot of energy. Too close, you don't have it. And too far away, the orbitals can't interact with each other. In the last video and picture, we showed two s orbitals coming together, which is the top one right there. And again, when they come together, there's going to be some ideal distance between the two nuclei centers. That's the best savings. And as a Lewis structure, we would draw just H-H, where again, the line is the sigma bond. So all of these are sigma bonds, single bonds, all right? And they come together from the overlap of two orbitals. And what we're looking at there in the top one then is two s orbitals coming together. But you don't have to have two s orbitals come together. You can have one s and one p orbital coming together. You can also have two p orbitals coming together. As long as you have that overlap of the orbitals, you're going to do it. So hydrogen monofluoride, HF, the second example, comes from an f orbital, and we're using a p orbital here because if you remember, fluorine is a 1s2, 2s2, 2p5. Two p's can hold up to 6. That means one of the two p orbitals has a single electron. And if you're going to make a sigma bond, you need a single electron on the first atom interacting with a single electron on a second atom. So for HF, that's going to come from a 2p on the fluorine and a 1s on the hydrogen. And when that comes together, you make HF. So again, that's the Lewis structure. Fluorine shows the other electrons, the lone pair electrons. That would be the 2s2 and 2p4 of the 2p5. Those are the lone pair electrons. They're not interacting with the bonding. It's only that one singly occupied 2p orbital which interacts with the s orbital on hydrogen. And then the last example is just something like F2. Now again, fluorine, if you did the Lewis structure for F2, you'd have 7 valence electrons on each one of them, 14 divided by 2, 7 pairs, distribute them around. That's the structure you're going to get. In F2, you would have two 2p orbitals coming together, each of them having one electron, and they smash together, and this kind of bigger blue part right here shows the smashing sigma, if you will. Anyway, that would be that. And up here, by the way, I didn't mention it, but this would be the sigma of the 1s interaction, and then I would argue that this right here is the sigma between the 1s and the 2p interaction. But again, sigmas come come from orbitals smashing together, sticking in it. Those are all ways to make sigma bonds.